The objective in this lesson is to factor a sum and difference of squares. Sum of squares. Can a sum of squares be factored? Well, the answer to that question is no. A sum of squares cannot be factored. What is a sum of squares? When you have two perfect square root terms that have a plus sign between them. For example, the square root of the first term is x. The square root of the last term is 2. Let's say we said that it factors into x plus 2 times x plus 2. Well, we can check and verify that by simply foiling it out, first, outer, inner, last. And what we'll wind up with is x squared plus 4x plus 4, which does not lead us back to the original polynomial. So therefore, there's your proof that a sum of squares cannot be factored. What about a difference of squares? Can we factor a difference of square? A difference of squares is when you have two perfect square roots with a minus sign between them. And the only way you're going to factor that, because that last term is a negative, is that one sign has to be negative and one sign has to be positive. So let's see if that factors into x plus 2, x minus 2. So using FOIL, first, outer, inner, last. Notice outer and inner are the opposites of each other, therefore they will cancel out, which leaves me back to the original binomial I started with. So there's your proof that yes, you can factor a difference of square, but no, you cannot factor a sum of squares. Therefore, a sum of squares is prime. The only way you can factor a sum of squares is if the two terms had a GCF in common. Then you would take the GCF out and proceed with factoring if possible. Here are examples of sum of squares, all of which are prime because they cannot be factored. A difference of squares. A difference of square is one perfect square minus another. So here we have a squared minus b squared. So both of those are really what you call perfect squares or perfect square roots, because if you take the square root of a squared, that's a. The square root of b squared is b. So what you have is both a and b that will be in two binomials, a plus b, a minus b. So in other words, it will always result in two binomials that have the same numbers, same factors inside. The only difference is their signs. One sign will be negative and one sign will be positive. Let's do an example. So here we have x squared minus 16. So I see I have two perfect numbers, so that would be perfect square roots. The square root of x squared is x. The square root of 16 is 4. So the two numbers I'm going to be dealing with is x and a 4. And all I need to do is place them in a binomial with different signs. So then what I'll have is x plus 4 and x minus 4. Does it matter in terms of which one is first, whether x minus 4 is first or x plus 4 is first? No, it does not. With multiplication, it's commutative, which means order does not matter. For example, if I had 3 times 5, that equals 15. Well, it's the same as if I put the 5 in the front and say 5 times 3, it still equals 15. So with multiplication, it's commutative, which means order does not matter. And there you have a difference of squares. Let's do some more practice with difference of squares. Here in the first example, we have x squared minus 49. The square root of x squared is x. The square root of 49 is 7. So that's going to factor into two binomials with signs that are different. So it's going to factor into x plus 7, x minus 7. Let's go to example 2. Here we have a squared minus 121. So the square root of a squared is a. The square root of 121 is 11. So therefore, that is x plus 11, x minus 11. So might I remind you that yes, when you're doing these difference of squares, you definitely need to make sure that you know your square roots so you'll know what numbers go inside the binomial. Let's do the last example. The square root of y squared is y. The square root of 4/9 is 2/3 because the square root of 4 is 2. The square root of 9 is 3. So that's going to factor into two binomials, y plus 2/3 and y minus 2/3. And there you have difference of square. Let's do some factoring where we have squared terms on both ends, the front term and the back term. So you're going to do the same as you're going to do with the numbers. Just find the root of them. The square root of 25a squared is 5a. The square root of 9b squared is 3b. So you're going to have two binomials with signs that are different. 5a plus 3b and 5a minus 3b. How about the next example? Let's find the square root of those two numbers. The square root of 36x squared is 6x. The square root of 49y squared is 7y. So you're going to have two binomials with different signs, which are going to factor into, you got it, 6x plus 7y times 6x minus 7y. Let's do the last one. What do you think that one factors into? I'll give you a moment. If you said 8m plus 5n times 8m minus 5n, then you are correct. Good job. Let's do some more practice with difference of squares. Factor each difference of square. Now the first thing you should always do when you're factoring is to check and see if there's a GCF, and if there is, then you must factor that out first. So looking at that first example, we want to look at the 5 and the 20 and see if there is something they share in common. So you look at a smaller number, which is 5, and you ask yourself, is there a 5 in 20? Yes, it is. So therefore, there's a GCF of 5. So let's go ahead and take the GCF out, and what's left goes in parentheses. Notice what we have left is a difference of square, and that's going to factor into x plus 2, x minus 2 with the GCF on the outside. Next, we want to look at the second example here. And even though these two are two perfect square roots, for example, the square root of 36x squared is 6x and the square root of 64 is 8. However, if we factor it that way, we're still going to have to factor it further, because step 1 is always first take the GCF out. So we're going to take the GCF out first. There's a GCF of 4, and what's left goes in parentheses. And now we can go ahead and factor this difference of square. The square root of 9x squared is 3x. The square root of 16 is 4. So that's going to factor into 3x plus 4, 3x minus 4, with your GCF on the outside. Okay, so remember, with the difference of square, you're always going to have signs that are different, but the factors that are inside will be the same, the numbers that are inside. So the last example, I want to go ahead and factor out the GCF. There's a GCF of 4 because there's a 4 inside of 100. So when we take the GCF of 4 out and write what's left, again, we are left with a difference of square. And what does that factor into? Well, if you said x plus 5y, x minus 5y with the GCF of 4 outside, then you are correct. And there you have the difference of squares with a GCF. I want to show you what happens if for some reason you don't factor out the GCF. Let's say you saw this and you weren't aware that there was a GCF of 4. Instead, you just took the square root of them. The square root of 4x squared is 2x. The square root of 100y squared is 10y. And so you wrote it as 2x plus 10y, 2x minus 10y. Well, the reason you would not be done with that is because both the 2 and the 10 have something in common, because inside of 10 there's a 2. And you're not finished factoring completely until the two terms have nothing in common with each other. They can't have something in common within their group. So once we take, for each group, take the GCF out and then write what's left in parentheses. This is what we're left with. We're still not done because I spy that we have, well, we don't have a GCF here because these two are totally different. But what I see here you have left is 2 plus 2 on the outside. And then what is left is x plus 5y times x minus 5y. And recall, that's the same answer that you got in the previous problem on the page before this one. So it's not a big deal if for some reason you don't find the GCF and you find a smaller number that they had in common. What's going to wind up happening is that you're just going to have to work the problem a little further until you are able to completely take the GCF out. So with this last form, I know the GCF is out because the x and 5y have nothing in common with each other. So you know now that the GCF has been taken out. And there you have it, factoring a difference of square completely. Factoring higher roots. In this problem, we're asked to factor this binomial, and actually this is a difference of square because I have two perfect squares with a minus sign between them. The square root of w to the 4th power equals w squared. The square root of 81 equals 9. So I'm going to have w squared plus 9 and w squared minus 9. And the reason I'm not done is because I need to look at these two binomials to see if they can be factored further. So if we take a look at the first one, this is what we call a sum of squares, which I covered earlier in this video. We have two perfect square roots because w squared is a square root. The square root of 9, that's a perfect square root. Two perfect square roots with a plus sign between them is a sum of squares. And recall what I said about sum of squares? Is that factorable? No, it is not factorable. So there's nothing we can do with the w squared plus 9. How about w squared minus 9, a difference of square? Is that factorable? Yes, it is. What does it factor into? If you said w plus 3, w minus 3, you're correct because the square root of w squared is w. The square root of 9 is 3. So that's w plus 3, w minus 3 with the sum of squares. Still part of your answer. You can't factor it, so you just leave it like that. And this is your answer. And there you have it, factoring completely. Let's do one more factoring completely. So step 1, I want to look at these two terms and see if they have anything in common. So I look at the smallest number, it's a 5, and you ask yourself, is there a 5 in 80? Yes, there is. So that means that 5 is going to be a part of the GCF. Do they both share a y in common? No, they do not. So the GCF then is going to be 5. So again, GCF on the outside, and what's left goes in parentheses. Now, what do you notice about what's left in parentheses? If you said it's a difference of square, you are correct, because the square root of 16y to the 4th power is 4y squared. The square root of 1 is 1. So that's going to factor into 4y squared plus 1 and 4y squared minus 1 with your GCF of 5 on the outside. Are we done? No, we are not. Can we factor the 4y squared plus 1? No. Why? That's correct, because it is a sum of squares. You cannot factor a sum of squares unless they have something in common. How about the difference of squares? Can we factor that? Yes, we can. And what does that factor into? If you said 2y plus 1 and 2y minus 1, then that is correct. So putting everything together, our final answer is GCF of 5 on the outside, then you have the sum of squares, and we factored the difference of square, and there you have it, factoring completely. Okay, that's it for this lesson. Thank you for watching MVP Tutorials by your instructor, Dr. Speights. I hope you'll join me in the next lesson. Please feel free to like, share, and subscribe. Goodbye for now.